As you know, if you've attended some of our Citrus ECS Frontiers in Technology seminars in the past, normally we'd be serving you up a burrito or a sandwich or a bag of chips. Maybe you're eating at home. If you are eating those bag of chips, if you could just stay on mute, that would be appreciated. We have a speaker today that's in line with Earth Week. So the 50th anniversary of Earth Day was this past week, and today's talk will focus a little bit on the role of information, informatics, remote sensing as applied to better understanding land use specific to the San Joaquin Valley. Our speaker joins us from a company called Land IQ, based out of Sacramento, but operating across North America, to my understanding. The speaker is Dr. Joel Kimmelshue. He's a founding partner and principal soil and agricultural scientist with Land IQ. His PhD's in soil science with a concentration in water resources. He received that degree at North Carolina State University, go Wolfpack, and has a certification as a professional soil scientist. With over 22 years of consulting experience, he focuses on practical and applied solutions for the development and management of agricultural-based soil water plant systems, and especially irrigated systems. And for those of you in the San Joaquin Valley know, it isn't green unless it's irrigated. So without further ado, I'll hand it over to you, Joel.
Thanks a lot, Josh. I appreciate the introduction, and welcome everybody. I'd love to see all your faces, but this will just have to do for today. I'm going to spend about 45 minutes talking about some of the work that we do, and with a focus on kind of the foundational component of how to make things accurate when you're measuring things on the landscape, and that's through ground truthing. And I'm going to introduce and discuss two larger projects that we have in our organization, one being mapping every agricultural field from Mexico to Oregon, and another one discussing how we measure and validate consumed water, the amount of water that's given off by crops on the landscape. So I'll jump right into it. And both of those topics will have a kind of a heavy spicing of ground truthing, which is kind of foundational to the work that we do. So first I'll talk about who we are at Land IQ and why we do the work we do. Then I'll break right into some land use work and some ground truthing stations that we have. I'll talk about some results of those two studies or projects that I talked about, classification of land use and estimation of consumed water by agricultural crops. We'll break into some precision accuracy and validation components, how we measure how accurate we are. And then I'll talk about how we're going to integrate more districts and more areas and more ground truthing stations in the future. Land IQ, just one slide on us. I used to work for a large engineering consulting firm. I'm a scientist, a soil scientist in particular. And a colleague of mine and I decided to start our own little organization back in 2007. With 5 people and 35 people later, we sit here now with an office in Sacramento and one in Los Angeles, smaller group down there that does ecosystem restoration work. But we purposefully developed our organization with 2 main technical disciplines. I call them land-based scientists and spatial scientists. And we marry the 2 together. Our land-based scientists inform our spatial scientists, our remote sensing folks, our GIS folks, what's going on the surface of the ground and what's meaningful for their work. And vice versa, our spatial scientists inform our land-based scientists, hey, if you want me to do a really good job in remotely sensing this component on the landscape, I need these type of ground truthing data, I need this frequency, I need this reliability, etc. And so it's a really neat marriage of those 2 technical disciplines. We also have a development side of the house in which we no longer rarely do we produce hard copy reports with maps and text and such. Most of our deliverables now, because all of our work is spatial in nature, is delivered via portals, web portals of various kinds. And I'll touch on that just briefly. So I'm going to jump right into the first topic or first main project that we do. We work for the state of California Department of Water Resources. And according to state law and the Sustainable Groundwater Management Act, the Department of Water Resources is required to provide consistent land use across the entire state, in particular agricultural land use, because when we're talking about water, if it, as Josh said, if it isn't green, if it isn't irrigated, it's not green. Or if it's green, it's irrigated, especially in the Central Valley. So we developed a heavy ground truth approach and a really robust and kind of complicated but accurate remotely sensed approach. And what we do is we delineated and continue to update these delineations over 380,000 different fields in California. Those fields are 2 acres and greater, and they are a homogeneous land use or a homogeneous crop type. And I'll talk about that a little bit in more in the future. But just for your happy hour conversations, here's some interesting stats for you. That agriculture in California, from Mexico to Oregon to Nevada to the Pacific Ocean, is, according to our classification, about 9.5 million acres. Urban, the footprint of urban, we map urban areas to the outer boundary of all the urban areas. That's about half again as much, larger than I expected when we got going on this. I figured it'd be about 10 or 20% of agriculture, but the footprint of urban is about half again as much as agriculture. Then managed wetlands, we map those too, and those kind of vary from year to year. Our agricultural mapping, I'll be focused on that specifically today. It includes both irrigated and fallow fields, but only the irrigated portion of every field. We do not include farm shops, farm roads, equipment pads. Anything that's not irrigated is not in the boundary. So it's truly the irrigated area of every field. I'm gonna go through, we do it for California Department of Water Resources, and they're split into 4 regions, and I just have 4 slides here of our 2014 mapping. I'll talk about in a minute where you can go and pull down the publicly available free data of our mapping through DWR in a second. But we'll just go north to south. And this is kind of the major crops in the north include what I have listed here, and the total irrigated and idle land or fallow ground when we did this classification scheme was about 1.5 million acres. And if we move further south, we'll go to the north central region where there's grapes start to become a popular crop, as you might imagine, in Napa and Sonoma counties, and also in the Northern Valley area. And the total irrigated ground, almonds and walnuts and alfalfa, and quite a mix of crops. You see the legend there. It's about 1.6 million acres. Now we go to the big boy of them all. That's the south central region, and that includes the majority of the San Joaquin Valley and also the Salinas Valley, and there's a whole suite of crops that you can see there. About almost 5 million acres of crop ground there. And then if we migrate further south, we see the southern region, and that has even more unique crops, including citrus avocados and some unique coal and truck crops and things like that. It's almost 1 million acres. So again, how do we do this work? There's a number of steps that go involved in this. One is we have very, very detailed field boundaries, as you can see on the image on the right-hand side. We delineate anything that's 2 acres and greater, and yes, it's all hand delineated. It's not, we have to have these very, very accurate field boundaries. So it's quite an undertaking to delineate those. We have a lot of interns that do that and continue to update those, but once you get it done once, it's an update process. We have to have those field boundaries that are really exact so that when our remotely sensed approaches kind of scan the image, we reduce the amount of what we call confusion or error. We want to look at a homogeneous crop type. Our overall accuracy is 97.6% on our last classification. How do we get that? Well, first off, our legend is about 50 crop types, which represents about 98% of the total irrigated lands in California. So back to how do we get our accuracy? I'm going to touch a little bit on ground truthing here for a second. We put a crew of people in a vehicle, an SUV, and we drive about 14,000 miles every year in the state of California. We tailor those ground truthing efforts as related to where we know single, double, triple, and quadruple cropping occurs, and our frequency of return to those fields is based on those cropping systems. We have 2 people on iPads, one on the left side of the road and one on the right side of the road, and we use that information as a subset of the total cropped area. We are on public roads, so we capture about 10 to 12% of the total irrigated ground in California at key times, and we do that with iPads with an image base behind it and our polygons, and then we drop points. We say drop points in those polygons. What's that crop? So we use that data set for 2 purposes. We use that for validation or calibration and validation. So if we know it's an almond orchard and we've captured 5,000 almond orchards, for example, we can then create what we call a fingerprint of almonds. That fingerprint is useful to, what I say, dust the rest of the crime scene, which is the areas that we didn't drive by, and to statistically and probabilistically determine what's the probability that that area that we're dusting that we didn't drive by is an almond orchard. So we match fingerprints basically. So with literally tens of thousands of data points, we've been able to create fingerprints for almonds and walnuts and pistachios and alfalfa and corn and a whole suite of different crops. We still conduct all the ground truthing every year, all the time, but that's the robustness of this ground truthing. We collect, tens of thousands of data points every year. That is how we can get the accuracies that we do. These accuracies are really critical because we're talking about cropping systems. We're talking about the biggest water user in California, agriculture. So and if we're going to tighten up how we manage our water resources, it's awful good to know what's going on the surface of the ground and how that may be changing, and it is changing rapidly. I'll move on. Currently publicly available, and I'll share a link with you, I think on the next slide, is the 2014 main season cropping year and the 2016 main season cropping year. Since we did those cropping systems, we're now doing what we call water year multi-cropping and or hydrologic year. Basically, we start in October, like for example, the 2018 hydrologic year begins in October 1st, 2017 and ends September 30th, 2018. And that's because it kind of mimics the hydrologic year of when we begin to get rainfall and such. That information is now, we're done with that classification, the 2018 hydrologic year. Hopefully DWR will be publishing that soon, so you'll have 3 data sets. The difference between the 2014-2016 versus the 2018 data set is the 2018 data set contains multi-cropping. So my slogan now is all crops everywhere all the time. The crop maps are really fascinating if you're into something like that. We're conducting the 2019 hydrologic year right now and are hopeful that DWR will extend into the 2020 hydrologic year. So I talked a little bit about accuracies, and this is an accuracy matrix. So it's observed versus predicted. What did we observe versus what did we predict? And this is a crop by crop accuracy matrix with what we call omission and commission errors. How many times did we get it right, basically? And you'll notice that, like for alfalfa on the upper left-hand corner, on the bottom, actually, we saw 400, we set aside a subset of our ground truthing data for validation, and we set aside 497 alfalfa fields. Well, we got it right 474 times. But wherein we didn't get it right, what was it? And you can see where sometimes we got it wrong. We're never perfect, that's for sure, but we try to achieve as high accuracies as we can. Here's the slide that talks about where you can go get that statewide crop mapping data. And that can be found on this website you can either use the link here or you can just Google DWR land use download and you'll find this link pretty quickly. So you'll see our mapping there. You'll see also some historic mapping that you can get. You can look at it on the very bottom of that image on the right-hand side. It says California DWR land use viewer. That's what it says it is. It's a viewer. You can view all the data. and you can download it from there as well, I believe. But this would be the main source in which if you wanted to download the data and start to fiddle with it. And keep an eye on this because DWR should be updating to 2018 fairly soon. Okay, so that's land use. That matters. Okay, because why does that matter? Because again, like I said, if you know what's going on the surface of the ground, that's very meaningful for a variety of things. In this case, we're talking more about consumed water use. That's also meaningful for marketing of crops. It's meaningful for land use change. It's meaningful for carbon sequestration and permanent crops. It's meaningful for air quality concerns. It's meaningful for water quality concerns, groundwater suitability of what crop is grown where and over which what groundwater quality does it lie. There's a lot of things that a nice land use data set can be used for. So let's take that land use and we'll shift over a little bit here to evapotranspiration. I'll call it consumed water. How much water do the crops that are growing on the surface of the earth in California and elsewhere for that matter, how much water are they using? That's a tricky thing. You can't see it happening, right? Evapotranspiration necessarily, you can't see it happening, but it's important to understand that because it is the biggest water user in California and our water resources are stretched, and it's meaningful to get that type of estimate of the water that is evolved or evapotranspired by the crops into the atmosphere. Another way I like to say it, it's the water that leaves the water balance on the surface of the ground. We'll break right into it. So we use what we call an energy balance approach. There's lots of references to this in the literature. I won't go into grave detail about all these components, but the one thing that we differentiate our work into, again, is heavy ground truthing. I'm sorry to say that so many times, but we really believe that's critical in more accurately estimating whether it's land use or consumed water or whatever it might be. Heavy ground truthing is important. Is it hard? Yes, it's hard. Does it sometimes cost more a little bit? Yes, it does. But these are meaningful things when water is selling for anywhere from $200 to $1,000 per acre foot of water. It's a huge investment for irrigation districts, growers, water managers, etc. The cost of this work is dwarfed in comparison to the value of the water. We have done this work for a number of years. Currently, we're in the South. We're doing a number of places, but our most active projects right now are in the South Valley. That's Kern County, Tulare County, a little bit into Kings County, some work in the Delta, etc. We use different approaches depending upon the client, but the approach that I'm going to talk about today is what we call our data-driven model. And it's driven again by heavy ground truthing for calibration and validation of the results. We look at it from a spatial approach to recognize field by field differences. This is called remotely sensed evapotranspiration. There's a number of models out there that you can use to do this with, but most all models, I say, look from the top down, whereas ours builds from the field level up. I'll just leave it at that. So the 4 polygons that you see on the right-hand side of the screen are 4 basically irrigation districts. One's an annexed area. The small one in the middle is the annexed area of the district immediately above it. The stars on the district represent our ground truthing stations. So in this case, our ground truthing consists of, rather than driving by fields and dropping points on an iPad, this consists of actual meteorological stations on the ground that are measuring with the instrumentation that we need to measure parameters that allow us to calculate actual ET or an estimate of actual ET for that field. Currently in this area, we have about 40 locations and different types of stations. We have some that are more costly, that are more heavily instrumented, and then some that are less costly that are provided for repetition or repeatability across the landscape. Those actual ET values from those ground stations are used again to calibrate our ET models and ultimately validate them as well. So here's a map that you may be able to understand a little bit more, kind of where we are. This is a blow-up map of where we were before. So those districts that you see on the south, they're the ones I just showed you. And then we're instrumenting more stations in the northern part of Tulare County and actually outside of Kings County to the west. These stations are a collaboration that we're conducting right now with UC Davis and Dr. Daniele Zaccaria and Dr. Rick Snyder as well. And so we're maintaining their stations in return for data usage. And the area of Tulare County that is in between the stations on the north and the stations on the south is also, now we're populating that entire area. It's about 500,000 acres in there for the TULE subbasin area, which is comprised of 6 groundwater sustainability agencies, which are groups that are in existence to comply with the Sustainable Groundwater Management Act. Okay, so here's some of the stations that we use. Again, ground truthing, we're measuring things on the ground, actual measurements on the ground so that we can inform, calibrate, and validate our models. We have some different types of stations, depending again upon cost and need to repeatability. We work with an organization called TULE Tech that has some lower cost stations that work really, really well in grapes and almonds and some other permanent crops. And some of the stations, like the one on the lower right, provide you with an idea of the types of things, instrumentation and what we're measuring. We work with growers in that. We take that calibration data and work with our remotely sensed models in a number of different image platforms, primarily Landsat 8, which is acquired once every 16 days, but also Sentinel-2, which is a higher resolution, no thermal band, but is more frequent, once every 5 days. Then we also have a contract with Planet Labs to get a monthly mosaic of information from them. These are some of the parameters that are measured from the instrumentation on the station itself. And these are some of the parameters that we need to calculate actual ET on the ground. We've modified those stations according to the crop type that's necessary, that we're working in, get it out of the way of the growers that are trying to do cultural practices between the rows, get it at the right height, and still kind of streamline the monitoring, but it's really important to make these measurements. So again, calibration, validation, ground truthing matters. TULE Tech, again, is one of the stations that we use. They're very, very valuable from the standpoint of grapes and almonds and pistachios. And then we have, all of these stations are telemetered. So we have a number of phone numbers, basically, that we pull in the data every day, well, every 15 minutes, actually. And we have set alarms or flags to say if the data falls out of a certain range, it alerts us that something may be going on in the station. It's critical because we can't just go out, change out data cards every 2 weeks, and all of a sudden we've lost 2 weeks of data because we didn't know something was going on. So all those are telemetered back to our servers in our office. What do we provide to our clients? So let's talk about one irrigation district in particular, water storage district on the north end of Kern County called Semi-Tropic Water Storage District. There's a number of irrigation districts that we provide this to, but I'm going to give one as an example. Within 30 days of the prior month, we provide a field-by-field consumed water. So how much water did your 80-acre alfalfa field in the month of April consume? You get to know that by May 30th. And every month we deliver that, both in kind of standardized reporting format, tabular data, and also spatial data. We're a spatial-heavy organization. So GS files are delivered as well for folks that want to use GS technology to further interpret the data for their purposes. We provide an accuracy assessment each month, and then at the end of the year, we'll roll up all the monthly reports into an annual summary report. So I'm going to run through a year's worth of data. I probably could have put in 2019, but this is 2018, but you'll get the idea. On each slide, it's kind of most interesting to look at the color change on the left. And this is kind of a good way to understand the water demand in a system, right? As things heat up, the demand or the evapotranspiration of water in crops increases as well. You'll notice some areas of, this is Semi-Tropic Water Storage District, you'll notice some areas stay dry. Green will be highly fields that are consuming a lot of water, and red and orange will be areas that basically stay dry. And this is, again, back to Josh's comment to start off with. If it's green, it's irrigated. In this map, if it's green, it's irrigated. That's true. But not everything is irrigated, and some areas are natural areas. Sometimes you'll see water flow coming across the landscape. Sometimes you'll see where growers decide to fallow their field, not irrigate it for that year. But I'm going to run through a year's worth of data, and then I have a little animation, I think, after this, and it kind of does it by itself. But here's January, there's February. You start to see things kind of heating up, if you will. April, May, now we're starting to get heavy into the irrigation system. You can start to see the fields that are irrigated. June, you can absolutely see the fields that are irrigation, partially irrigated, field areas that are not irrigated off to the west. July, August, okay, things are starting to cool perhaps a little bit. There's a lot of almonds grown in this area, and in August is harvest time, and they kind of stop irrigation at that point in time so they can have field access and traffic, they can get into their fields. September, may I hit it again with a post-harvest irrigation. October, November, and things start to cool off, and you almost come back to where you were again in January. So this is the overall map. In the stats on the right-hand side said, so our results said the maximum field, forget the maximum pixel, we'll talk about it at the field level. The maximum field in 2018, somewhere in that district, consumed, evapotranspired 56 inches of water. You stacked 56 inches of water on top of the ground, the maximum field consumed that. The average field consumed about 28.3 inches of water. That includes fallow fields too, which consume a lot less. So you get the idea of the range that we're talking about here. So here's an animation. Hopefully it's moving through the lines well enough to show that to you. We'll try it again. So the same slides that you just saw, but kind of animated to give you an idea of the change over time. This is a graphic of a neighboring district, but basically the same curves. Maximum field, this was for 2019, well, a sum of 2019 and 2020. Maximum field was about 56.6 inches, and that's the maximum. Let me clarify that. That's a maximum field every month that we do the analysis. So the maximum field may change from month to month. So that's truly, that's elevated because we're picking up the max field every month, not just one field. So it's the sum of the largest fields every month. And then the average field is about 32.3 inches in sum of 2019 and 2020, which is a lot higher than the semi-tropic area because we have a lot less fallow fields in this area. And then this is another graphic to kind of show that demand curve over the calendar year. It's a classic demand curve, excuse me, as you go through the year. And I put up, 6 of the peak months during the growing season to give you an idea. I'm going to couple back again here now with our land use. So the way we do our work is we care about land use. It's informative to know that, oh, these fields are all almond orchards, or these fields are all alfalfa fields, or whatever. You can refine your analysis, your remote sensing analysis, if you know what range of ET you're supposed to probably be working in with the crop type that's there. So we constantly update land use and use that in our analysis as well, not just looking across the spectrum of the entire landscape of the lowest ET area and the highest consumed water area. There's another example of a crop map from another district that we work with. We bin by crop type. We recognize the unique crop type consumed water attributes. We integrate also permanent crop age. I'll talk about that in a minute. And we're beginning to analyze and integrate the component of permanent crop density. To a point, the more trees or vines you have per unit area of ground per acre does influence consumed water to a point. Okay, so let's talk a little bit about validation against actual and repeated field measurements. So why do we do all this ground truthing? We want to be able to compare to what's going on the ground to what we predict, actual versus predicted. We, as I mentioned before, incorporate multiple lines of evidence, permanent crop age, permanent crop density, and other unique field conditions. So you may remember that I said we map every crop in the state of California, which we do. So we pull out all the permanent crops: almonds, walnuts, pistachios, prunes, peaches, nectarines, grapes, etc. And we have a separate analysis that we conduct where we look backwards in time at images to where that fingerprint of an almond orchard, walnut orchard, pistachio orchard, etc. changes from the fingerprint of that crop to the fingerprint of bare ground. If we know when that fingerprint changes in the year, we can say, ah, great, so the fingerprint changed, that must be the year that it was planted. And indeed, we've validated that through looking at some historical imagery. So now we know the age of every orchard. There's a direct relationship between consumed water and age. Smaller trees consume less water than older trees do. I'll show you a graphic of that in a minute. Tree density. This is some work we've done where over time we've noticed, and as crop scientists, agronomists, that man, they're putting more trees in per acre. And that's a general trend. The purpose of doing that is to try to get more production per acre, obviously. But what comes with that is an impact on consumed water, influence on consumed water, to a point. Once the canopy closes in, the canopy closes in. It's not necessarily true how many trees you have at that point. We do some mapping on irrigation type. So depending upon how you irrigate, whether that's furrow, border check, drip, flood, sprinkler, has an influence also on consumed water. There's more efficient irrigation methods than others. We use a number of different, what we call, lines of evidence to determine irrigation type. Once we've mapped the field as a certain crop, there's a lot of attributes you can tie to that field once it's mapped. We also look at comparison to applied water. We have some meter data, and in most cases, you better make sure that your applied water is greater than your consumed water, because some of that water that's actually applied on the field isn't 100% utilized. It's past the root zone or runoff or whatever. So your applied water better be greater than your consumed water. We also think about things that's what's reasonable. Are these reasonable numbers? And we employ our agronomic knowledge to look at it. Actual versus measured, as I mentioned before. So here's kind of some different things that we look at. This is some data from one of our stations on what we call a huller field. It's a fallow field. It's a huller pad. There's nothing grown there. We want to recognize that lower end of the spectrum of consumed water, which is not irrigated. Only thing that is consumed off of that huller field or that dirt pad is rainfall. So when we look at things across time, we want the data from our stations to be tight to an expected number. Well, during August, September, October, up to the beginning of November, we didn't have any rainfall in this certain situation. So it better be close to zero. And so we like to see our data kind of bounce around zero, which is important. If it bounced around higher than some of the thresholds we put on this, we would get a flat, like I said, get an email or a notification, hey, you're getting an inch of ET, something's wrong when the huller field, when it hasn't rained. This is an almond orchard. You notice the vertical scale has changed in that the evapotranspiration is actually occurring. These are half-hour samples with similar conditions, constant similar conditions. We picked this time range because we want to say, okay, if all these conditions are similar, our evapotranspiration better stay kind of constant along the line. So we look at these things from a precision standpoint. This is a graph of mean evapotranspiration by tree age. So for almonds and pistachios. So we took all of the large areas that we look at. We know the age of every tree, or of every orchard, and we know the mean evapotranspiration of that orchard. And then we summed them together and took an average based on the number of orchards that are 21 years old and the number of orchards that are 15 years old and 3 years old. And these are the curves you would expect to see. As an orchard grows, almonds tend to get to maturity around 6-7 years, pistachios around 10 years, and then they kind of flatline or plateau at the top. And we know that almonds tend to consume more water than pistachios do. So when we plotted this, we were very pleased with these results as to the trends that we saw. This is just a couple years worth of ET data by crop type, and these are very reasonable. This gets back to what's reasonable when you're looking at the data. Understanding your data is really important and what you should be expecting. And so these are a couple years worth of crop type, and you'll notice in most cases, with the exception of the Shafter Station ETO, all of our consumed water in 2019 were just slightly lower than what we experienced in 2018. And that is due to the fact that 2019 was just slightly cooler and we didn't maybe have as much wind during that year than we did in 2018. This is a graphic that just shows basically applied water versus consumed water. The green lines are consumed water, and the black and the gray bars stacked on each other are the sum of rainfall and delivery. And that information tells us that we, like I mentioned before, our applied water, or our total applied water, which you should also be thinking about applied water from the sky, precipitation, should be, in most cases, higher than consumed water. We plot, try to do predicted versus observed. Again, what did we see versus what did we predict? These are kind of, this is a one-to-one relationship. This is not an independent validation. We included all the data in this. We didn't quite have enough stations to this, but still we use this as an indicator on how well are we doing. Are our predicted versus observed measurements lining up fairly well, and indeed they are. This is a testament to ground truthing. If you don't have any ground truthing data, you can't do these types of evaluations. Okay, this is a really interesting series of figures. This is 14 days. Each one of the curves is a day of raw alfalfa ET. So we have a station in an alfalfa field. You saw it earlier in a picture. And these are the peak ETs for 14 days. And you'll see some interesting trends in these curves. And the second day, where you have that jagged peak, the peak really isn't there. What's going on there? You might think, well, is my instrumentation faulty? Am I not measuring things or collecting data correctly? So we said, well, maybe we had cloud cover on that day. So that was our hypothesis, that was cloud cover. And then on days 3, 4, and 5, we saw a definite decrease in the peak ET. And we said, well, that probably is that the grower went out there and cut his alfalfa for baling. That was our hypothesis. And then these are days 8 through 14, the next 7 days. And we saw a gradual increase in consumed water through day 13. We thought, well, if he did cut it, then it's probably growing back. And then day 14, we see a peak that shows, wow, it's a really lot higher peak. And we hypothesized, well, maybe he irrigated. We're seeing water on that field. So on all of our stations, we have cameras. And I'm going to share with you a shot of every day for each one of those days. And the orange arrow represents the day. No, the earth is not tilted. Our camera is. You'll notice on the bottom, it was 104 degrees Fahrenheit on the bottom right-hand side of this figure. Very warm day in July, which is not uncommon for that part of the world. So that's the day we had full vegetative growth, high peak ET. Next day, we hypothesized, you may remember, that this was cloud cover. Indeed, it was. So we can show that. Then the third day, still really high ET, a little cooler, 92 degrees Fahrenheit, peaks a little bit less. Then lo and behold, the grower came in on the 4th day, cut it. That cutting begins to desiccate. Some of the growth between these small windrows begins to come back. You'll see that in the next few photos. It's beginning to get greener, further desiccation. Some of the greens coming back, further desiccation of the windrows. Then the grower fully windrowed it. And you'll see these peaks as we go forward. Watch, well, he windrowed it. The green starts to come back between the windrows. Then he baled it. You're getting more green coming back, etc., continuing And then on the 14th day, you'll see in the lower right-hand corner of this figure, you'll see some water coming across the field. So again, we use all this information as lines of evidence to try to inform us, tell us what's going on. Now we're confident in these results and we can apply them to other alfalfa fields where we don't have stations. I talked about this map before. So all these dots represent where we have stations. And then this is semi-tropic water district. I'm going to show you just the areas that we're now instrumenting in the northern part of Kern County, southern part of Tulare County, and part of Kings County. So all this information is great, but what can it be used for? Kind of in conclusion, Sustainable Groundwater Management Act is a monumental act as it will impact agriculture, already has started to impact agriculture. The purpose of the Sustainable Groundwater Management Act is to sustain groundwater. That meaning keep groundwater at a static level so we're not overdrafting it. Well, if consumed water or evapotranspiration is the biggest output of that water balance, we better try to measure it as accurately as we can. So what comes with the Sustainable Groundwater Management Act is a plan that a groundwater sustainability agency puts together. That plan is issued to Department of Water Resources, say this is how we're going to manage the surface of our ground to maintain our groundwater levels. And the use of that information that we create is for that purpose. There's a lot of groundwater modeling going on, and that groundwater modeling, the groundwater modelers really appreciate accurate data if they can get it. Simply irrigation district water management. If you know how much water you're consuming on a month-to-month basis, you're coming up to the end of the year, you're short, you're long, you can manage your water better. Some irrigation districts are now even billing their growers not on the amount of water that's delivered to their field, not on the amount of acres that they irrigate, but rather on the amount of water they consume. That's kind of like a water meter in your house. You can look at historic information for future water management, crop mapping, permanent crop age. I talked about those things. And we also offer up some web platforms like I mentioned before. I'll have one slide in a second, I think. I already talked about our deliverables. We deliver both tabular and spatial data, standardized monthly reporting, etc. This is the web portal, grower portal, and a different project that we're doing where a grower has a login, a username and password, and that grower can go in, he or she can go in and look at their individual fields and see how things are going. This is a yield decline portal. We develop portals for consumed water. We develop portals for change in water use, change in land use for Department of Water Resources, etc. But in conclusion, it's just critical. Ground truthing, we believe, is critical for measuring things accurately. And especially in light of water management challenges in California, increased regulatory compliance requirements in California, all for the right reasons. But with that, those land and water resources, which are critical to life in California, and people eating food and managing water appropriately, it's awful good to know how to monitor and measure the change of those couple resources. Not going to go into this too much, but that's kind of my concluding statement. And I'm happy to entertain any questions that anyone may have. And I may not be able to answer all your questions, but some of them possibly.
Yeah, great. Thank you so much, Joel. It looks like, yeah, we do have quite a few people in the room. So either put your questions into the chat box or you can raise your hand. I had a question, if you could go back one slide. You had mentioned here the coupling the remotely sensed ETA with some of the land use, but you've also shown that the land use tends to be pretty stationary at that point. So would you say, like in terms of investment, is it better to have more field stations if you were going to do that, or in more remotely sensed data?
Well, there's a balancing act between if we had all the money in the world, if our clients had all the money in the world, we'd put a station in every field, right? But they don't, and so there's a balancing act between accuracy, and every time you put another station down, you get just that much more accurate. So there's a balancing act between cost and accuracy, you know, different entities are interested in more accurate results than others, quite frankly. The state of California, for example, we are contractually committed to providing them with a ag land use database that's at least 95% accurate. So we have to do those really aggressive efforts in ground truthing and field boundaries and manual interpretation and automated interpretation to reach those accuracies. So to answer your question, it's usually a balance in the real world between cost and accuracy.
Yeah, that's great. There are two questions. Professor Kurtz has one about how do you measure the reflected irradiance, which I think you'll answer with respect to the remotely sensed data. And then Lorenzo follows up with the image classification and which methods have better performance, supervised, unsupervised, deep learning, and what are some of your methods?
I'll answer the last question first. The performance of a methodology, we used absolutely supervised classification from our ground truthing. We inform our methodologies from as much ground truthing as we can acquire. Our processes for land use classification include both automated and manual approaches. We first run things through an automated approach, and then we have what we call trained eyes, basically people that are agronomists that know what crops look like on an image from one crop to another to validate, further validate the automated process. And not every almond orchard looks the same. You can create a fingerprint for them, but that fingerprint isn't 100% accurate. So you have to have somewhat of a manual process to clean up some of those fields in the end. And I forgot what the first was.
Measuring the reflected irradiance.
I'm going to punt on that one. I would probably refer that to our agroclimatologist if he were here. But I can show you again the types of instrumentation that we have on our stations. Probably the net radiometer on the upper left-hand side, but I'd have to refer that to our agroclimatologist. I'm not going to guess too much.
And is this one of the TULE systems?
No, this is a more robust system that's developed. TULE system is a proprietary system that they've developed mostly for irrigation scheduling, but it does calculate actual ET, so we can use that information. And that's on the top picture here.
Okay, Vicky has a question. How are misclassifications of land use due to saplings handled? And can you elaborate a bit more on the method for determining orchard age?
Yeah, sure. So we call those young perennial saplings or recently planted orchards. And the bottom line to that is, in our remotely sensed approaches, we can tell you it's a stick sticking out of the ground, but we can't necessarily tell you what it is, depending upon how old it is until about the third year. So we can begin to differentiate between walnuts and almonds and pistachios and prunes and things like that about the third year. But prior to that, you know, remote sensing, I guess if you had centimeter resolution imagery, you might be able to do that. We do, because we capture so much ground truthing data, we do have a representative distribution. We'll drive by a young orchard that's just planted and we'll be able to tell you, because we drove by it, that's a walnut orchard or a almond orchard, and we'll log that information. So we'll have a representative distribution of young orchards, and is 60% almonds and 20% walnuts, et cetera. So you can apply that to numerical acreage numbers, not necessarily spatially, because you don't know where those young orchards are, other than we know it's a young perennial orchard. From an age perspective, the kind of the high level approach that we use there, that once we've classified everything as a orchard, perennial crop, we simply look back, we look at backwards in time at imagery with an automated process to see again where that fingerprint changed from a permanent crop, whatever that permanent crop was, to the fingerprint of bare ground, which tells you in that year or that month in that year, that's when that orchard, that ground was bare before it was planted. So then we know what year it was planted, therefore we can calculate the age.
Professor Medellin Eswara asks, how do you reconcile other data sets like the pesticide use reports, NAS, and other layers?
Sure. So we call those, thank you for your question, Jose. We call all those additional lines of evidence. We will sometimes overlay on pesticide use reports, but the challenge with that is, I believe they're at the section level and they're not spatially disaggregated any finer than that. And so what we do is we map every field everywhere. So, and it's a little more frequent, it's a little more timely, I guess, than pesticide use reports in that we're able now to deliver this within 6 months after the fact of the hydrologic year. So we will use the information kind of anecdotal information. We say, okay, we classified in this section of 640 acres, we classified 160 acres of almonds. What did the pesticide use report say? Did they say 165? Okay, good enough. That's good. Did they say 10? You know, so we use it sometimes in that regard. We're using it less and less. I'll be honest with you. The more times we do this work, the more confident we are, and our accuracies seem to increase every time you do it. But we will lean on it sometimes, sure. And the county ag commissioner reports, we may roll up our classification of crops to the county level and compare them. But again, usually we're in front of the release of that information, so we don't have the luxury necessarily to, when we have to deliver to DWR, that report many times hasn't come out yet.
Fantastic. We've got one last question, but I want to thank all of the participants today. By sticking around, you've made yourself eligible for a drawing for an ebook. So your name is being entered into a lottery, and we'll find out if you win. So Dr. Bernanke asks, what recommendations would you give to students interested in starting a research-based company?
Can you say that one more time?
What recommendations would you give to students interested in starting a research-based company?
A lot of antacids, that's important. No, seriously, I would suggest that you, research-based company, I would suggest you go work for one for a while, quite honestly. Learn how others do it. Just make sure it's really a passion for you in that area of technology. Many times, what you think you're gonna do when you leave college, you find something that's even more passionate for you, even though you thought you studied that in college. Not always, but sometimes. You know, be a sponge for about a decade, and if you still have the fortitude to try to go out on your own, I've really enjoyed it, and it is very gratifying and takes some time and effort, but there's pros and cons to every path in life. But just for me, it seems to be something I really enjoy. But yeah, I would, to answer your question, go out and learn from somebody, have a mentor, have a person that you can learn from for a while, because it takes a while to really learn the industry. I worked in a large engineering consulting firm for 12 years before I went out on my own.
Yeah, that's great. Well, we have some real-time results. Professor Coleman and Hope Hoptman, you are the two winners of today's drawing. So if you want to go ahead and shoot us an email about that, or put your contact information in the chat box, we'll make sure you get your prize. And I certainly encourage everyone to stick around if they have additional questions. Vicky Espinoza will facilitate a short grad discussion following this, so just stay on the line, so to speak. On behalf of the nearly 50 people in the room, thank you so much for joining us today. This brings to a close the third and final FIT seminar for the spring semester of 2020. So thanks for your participation, Joel. Really appreciate you taking time out of your day.
My pleasure.
Okay.